Continuing on with correlation, let's wrap up some of these ideas now that we have the basics down. So again, when we're thinking about direction, we basically think about two things, as long as there's some relationship shown. If it's positive, as one variable increases, the other tends to increase. And that keyword is tends to increase, because again, these are basically averages that we're working with. It's general trends. It's not always perfectly guaranteed. And if there's a negative relationship, as one variable increases, the other tends to decrease. You can call it X and Y. You can call it independent dependent variable. You can call it explanatory response variable. You just think of it in terms of two variables and how they move together. And again, we've got this idea of weak, moderate, strong. And so if the correlation is closer to 0, it's weak. If it's somewhere around 0.2 to 0.6, that's about a moderate, depending on whom you speak to. And a strong correlation, the magnitude is closer to 1. And remember, these can be positive or negative. So a moderate correlation, 0.2 to 0.6, or negative 0.2 to negative 0.6, something like that. And a strong correlation, say greater than 0.6 or more extreme than negative 0.6. Great. So for a correlation here with our temperature and coffee's example of negative 0.741, that is a fairly strong negative linear relationship between temperature and coffee. So as the temperature goes up, the number of coffee sold tends to go down because of a negative relationship. And very straightforward idea, which you've heard of many times before, I'm sure before this class, and that we have talked about a lot in other contexts. Correlation does not imply causation. So that's why everything we're doing, for the most part, unless there's some random experimental study that we have going on, everything is just going to be an association, a correlation. We're not claiming causation. Even if our language sometimes implies it, we need to keep in mind that it is indeed an association. So in this silly example here, as ice cream sales increase, say murder rates go up. And really the issue there is not that there's a causation between ice cream sales and murder rates, thank goodness, but instead the issue is temperature. So the confounding variable there is temperature. As temperature increases, so do ice cream sales. But also as temperature increases, so do murders generally, particularly in seasonal climates where temperature fluctuations correlate with crime fluctuations. So anyway, confounding variables, correlation, causation, ideas that you already have thought about in different ways before. And just some other little things to keep in mind. Yes, with correlation, again, that's why I don't get too caught up in this idea of one's X, one's Y in terms of our variables. I just think of it's two variables. So the correlation between coffee and temperature is the exact same correlation as temperature and coffee. It's transitive, basically, I think is the mathematical property. So it's a symmetrical situation. X and Y, Y and X, the correlation remains the same. It has no units. It's a unitless measure. That's why it's actually a very useful statistical measure, because it's effectively standardized. If I may use some lingo for a moment, it is the standardized covariance. And what that means is that it's put in units of standard deviations or units of variances, so that you can compare correlations, because all correlations are on the same scale. They go from -1 to 1. So correlations have no units, and regardless of how you change units, the correlation will be the same because it's a standardized measure. It's not based on units. And that's some more mathematical stuff. But All you got to keep in mind is that the correlation between two things is the correlation between two things, and it has no units. Okay, now we move on to linear regression. And I cannot do full justice to the depth of this topic in just a couple of videos or even just 1 week. This is why I teach a whole course on it. The course 5262, EPSY. We spend the first half just doing regression, and then we do something similar to it on the second half. So this will be very, very just basic information, and I'm going to try and hold back on giving too much detail because I really do love getting people excited about this topic. It's really powerful. It's really fun. It's often misused, and there's a lot of great stuff to it. So let me just dive in a little bit and say, what's the point of linear regression? Well, like I said in the first video, we've got some response variable, something we care about, and we want to use some other variable or variables. In this case, we're just going to stick with one. We want to use some other variable to explain what's happening with that response variable. We want to explain what's happening to coffee sales, in this case using temperature. And with the example here, we want to explain what a person's weight might be. We want to predict what a person's weight might be based on that person's height. Okay, for simple linear regression, just two variables looking for the relationship and how they relate between two variables. What linear regression is basically taking a scatter plot of points and putting on a algebraic line of best fit. If you remember back to Algebra 1, where you did that whole slope-intercept form and y equals mx plus b, an algebraic form, that's all simple linear regression is. That's all it is. So when we want to explain the relationship between two variables, we simply say, what is the best fit regression line that fits these data points? Whatever that line is, explains and captures the relationship between these two variables. So that's the high-level qualitative sort of explanation of it. The idea here is, how do we find this line of best fit? What are the actual mathematics, or at least what's the guiding mathematics behind doing this? Well, the way that the regression that we're going to use works, what the software does, what the program does, when you tell StatCrunch or R to give you the regression line to relate two variables, what it's doing is it's putting a line down between these points that returns the smallest squared vertical distance between the dots and the line. Again, what it's doing is it's saying, give me the line where it takes each of these red lines, each of these distances here, data point, regression line, data point, regression line. Take those distances, square them. There's a reason for that. Don't worry about it for now. And then add them all up. And then find the smallest distance possible. We call this ordinary least squares. And that's what we're doing. We are calculating, in a sense, a type of distance between the line we're putting down and the data. In this case, it's the squared distance between each data point and the line. We add up all those square distances, and we can take the square root if we want. But point being, just think of it as, I'm trying to put this line as much in the middle of these points as possible to minimize the vertical square distance between each data point and the line. There's a lot of math that goes into that, but we are not going to worry about that here. Feel free to ask plenty of questions about that if you want. I could talk all day about it. Okay. So connecting just to our algebra a little bit here, we know that anytime we put down a line like this, a straight line, it has an equation. And that equation has two parts. What are those two parts? Well, it has a y-intercept, that is the point on the y-axis where this line hits it. The point on the x-axis where this line hits it. That's the intercept. As we like to say in with our stats, when the x or explanatory variable is 0, in this case, it's not showing 0, but if this were 0, when the x variable is 0, what is the value of my regression line? What is the value of this basic simple line here? That's the intercept. And then this thing also has a slope. The slope just describes how steep the line is. And so the steeper the line, the higher the slope. The steeper the line, the higher the practical relationship between our two variables. The flatter the line, the smaller that practical relationship is, the smaller that effect of the relationship is. A perfectly flat line, no slope, means no relationship. Okay, so we've got a regression line, and it has an intercept and a slope. How do we actually get the numbers for these things? Where do they come from? Well, they come out from StatCrunch and they come out from R. And the next slide has a lot of information on it. So let's just go through the important parts. And you will practice this. Hopefully you've encountered it in the book. And it's just a matter of getting practice down a few times before I think it really lands into place if you're not comfortable with it the first time you see it. Okay, so we want to make a line here to explain the relationship between two variables. So the line, let me just show you what the line looks like for coffee and temperature. The line of best fit, the line that minimizes the sum of the square distances between the data and the line, is this one. This is our regression line right here. You can tell it's negative, so we'll have a negative slope, and it's got a y-intercept when temperature equals 0. It's got coffee sales right about here, so it's going to have an intercept right about there, right around 50,000, and some negative slope. Okay, so this is the mathematically determined best fit line. So what does our statistical output, when it makes this line, what does it give us? Okay, let's break down. There's more here than you'll need to know at this point, so let's just break down what things are that are here for now. Okay, the intercept, just like we talked about, is 49,337. Here's how we interpret it. When the temperature outside is 0 degrees, the predicted average coffee sales will be 49,337. Now the slope. And this is a little bit harder to interpret, but it's just like a mathematical slope. And here's how it works. Well, we say, and the slope here, the value is negative 553.7. What this means, for a 1 degree increase in temperature, we expect the average number of coffee sales to go down by 553.7. Remember, a slope is a rise over a run. So it's some horizontal change and then some vertical change. So we interpret a slope by saying, for every degree increase in temperature, how are coffee sales changing based on this line? We know that for every degree increase in temperature, there appears to be about an average decrease in coffee sales. Well, by how much? Well, by the slope. It's mathematically calculated to be that. So again, this means that for every degree increase in temperature, we predict an average decrease in coffee sales of 553.7. I cannot stress to you enough how this is all about averages. This line is predicting an average at every point. At every temperature, it's predicting what the average coffee sales will be. That's what it's doing. It's basically taking an average of the data vertically and making a line that best fits that. So again, the regression line is a line of average predictions. At every temperature, it's predicting the average number of coffee sales based on these data. We will pick up with the rest of this and finish up regression in the next video. Thanks.